How does nonlinear material behavior affect stress analysis? Have you ever wondered how materials behave under stress? The answer can be quite surprising, especially when we talk about nonlinear material behavior. This concept plays a significant role in stress analysis, which is essential for understanding how products might fail or break down. When we think about materials, we often picture a straightforward relationship between stress and strain. In simple terms, stress is the force applied to a material, while strain is how much that material deforms. For linear materials, this relationship is direct and proportional. However, nonlinear materials do not follow this simple rule. As they are stressed, their stiffness changes, which complicates the analysis. For instance, at low stress levels, many materials behave elastically, meaning they return to their original shape after the stress is removed. But as we push them closer to their yield point, they start to deform plastically. This means they won't return to their original shape, and their stress-strain curve becomes nonlinear. Metals often show reduced stiffness after yielding, while rubber-like materials can behave in complex ways, requiring specific models to describe their behavior accurately. Now, why does this matter? Well, if we're relying on linear stress analysis, we might get results that are either inaccurate or overly cautious. Nonlinear analysis, on the other hand, gives us a more realistic picture of how materials respond under load. For example, linear methods might predict higher peak stresses near stress concentrations than what actually occurs. Nonlinear simulations can show how stress redistributes due to plasticity, leading to better predictions. To tackle nonlinear behavior, engineers often turn to advanced analytical and simulation tools. These tools use finite element analysis techniques that incorporate nonlinear models and iterative methods. While these analyses can be more time-consuming and computationally demanding, they provide a clearer view of material behavior. Understanding nonlinear material behavior is also vital for failure analysis. It helps engineers predict how materials yield and deform under various loads. This knowledge is crucial for identifying where failures might begin, especially in components that experience high loads or cyclic loading. Nonlinear behavior is particularly relevant in areas like crashworthiness, where materials undergo large deformations, or in high-temperature applications where creep affects material properties. In product failure investigations, nonlinear stress analysis can explain unexpected breakdowns by revealing how materials behave in real-world conditions. In summary, nonlinear material behavior adds complexity to stress analysis but ultimately leads to a more accurate understanding of material performance. This understanding is essential for failure analysis methodologies and helps engineers design safer, more durable products.